Um, Today we're going to talk about multi-step problems and phase changes, and I'll tell you what both of those things mean. But I want you to first look at this example problem because if you just read it quickly, you might think it's exactly what we did last class. 20 grams, that's a mass of water. Okay, we know the CP of water at 35 is heated to 105. Find the heat absorbed or released. So Q equals MCP delta T. Easy, right? Plug in and we're done. But actually, it's not so simple. And the reason it's not so simple is because we are heating to 105. Now, there's nothing special about 105 other than the fact that it is above 100 degrees Celsius. Water boils or vaporizes at 100 degrees Celsius. That's a phase change. And so since we're crossing through the temperature of 100, right, we're going from 35 past 100 to 105, we're going to have a phase change. Something different is going to happen with the formula we use, and we can't just use Q equals mCp delta T. So for water, it boils at 100. We would call that its boiling point. Water melts or freezes, depending on which direction we're going. Are we putting heat in or taking heat out? Melts or freezes at 0 degrees Celsius. That's the melting point. So anytime we're working with water and we know we're crossing through the temperature of 0 or the temperature of 100, we're going to have some phase changes and we're going to do what we call a multi-step problem most of the time, unless we're just doing the phase change. Let me show you how that works. Okay, what I put below here, I'm going to use this graph to help me keep track of my work. They are the best way you can show your work for these problems and the best way you can make sure you don't make a mistake. Drawing this graph accurately helps you know that you have as many steps as you need in these problems. Below that, what I have here is this table of values. Okay, a lot of it might not make any sense right now, but we'll go through it. You'll always be given a table of values like this. For instance, we have water's melting point there, like we just discussed above, and its boiling point. You'll also maybe notice this liquid 4.18. That's the CP of water. Up until now, we've just been talking about liquid water. It's different if we have a solid or a gas. And then we'll also talk about what these HF and HV things mean. But know that this is always information you would be provided. So let's look at how I would approach this problem. We have water that's at 35 degrees Celsius. So on my graph, I'm going to do it in black actually, and I'm going to do some color coding throughout this lesson. That might be really helpful for your notes. If you want to pause here and get like 5 or 6 or 7 colors, that might be helpful. So our water is starting at 35 degrees. And we know we are heating it to 105. So those two temperatures should be on my graph. We also know, because it's water, that it's going to boil at 100. And since 100 is in between 35 and 105, we're going to be crossing through that temperature of 100. We're going to have a phase change. 0 isn't relevant here because 0 is below 35. So don't worry about the melting point. So what's going to happen, this left side of my graph is representing temperature in Celsius. And what we're going to look at on the right-hand side is heat or energy, or if you just want to call it Q, you can, like Q equals mCp delta T. As we start giving this water heat, it's at 35 degrees. As we give it more heat, so going more to the right on the graph, its temperature is going to go up. You heat the water up, its temperature goes up. The temperature will go up. It can only go up to 100 degrees though. Even though we want to get to 105, in this first step, the water can only heat up to 100 degrees. At 100 degrees, we're going to have to boil it, have the phase change, and I'll show you what that looks like. But that's our first step. Our second step, now that we're at 100 degrees, when we put more heat into this water, it's at its boiling point. It's ready to boil. Right now, here, it's a liquid. But we still need to boil it or vaporize it and turn it into a gas. That is going to happen with actually no change in temperature. which I know is weird, but that phase change, this would be a liquid to a gas, it would be boiling, it's at the boiling point. That's going to happen with no change in temperature, which is why it's a flat line. Once we've boiled it, then we can keep going. We can take that gaseous water and heat it up, in this case, to 105, which is where we're ending this particular problem. Like so. So we call these multi-step problems because in this case, we have 3 steps. 1, 2, 3. It's a multi-step. We have liquid water for this first step. How do I know it's liquid? Well, it's at 35 degrees. It's below the boiling point. It's above the melting point. In between the melting and boiling point, we have a liquid. So I have liquid water that when it reaches its boiling point, we'll boil it. It'll turn into a gas. And then I'll have gaseous water that I'm just heating up a little bit. Gaseous water is steam. So for these graphs, I put on my starting and ending temperatures. I put on the melting or the boiling point if they're relevant. And I know that at the melting or the boiling point, phase changes happen. And that's where we would have flat lines rather than diagonal lines. Then I can math it. So step 1 here, the one I labeled with the blue one, what we're doing in that step is heating liquid water. I can calculate the heat needed or the energy needed for that step by using mCp delta T. We have 20 grams of it. It's liquid water, so the CP is 4.18. And the change in temperature just for that step, we're going from 35 to 100. So do 100 minus 35 is how you'd always find the difference. That would be 65. And I can math that out. 20 times 4.18 times 65. I only did the temperature change up to 100 though, because at 100, the boiling point, it's actually going to stop changing temperature. And any more heat that I put into it is going to go to separating those molecules further and undergoing the phase change from a liquid to a gas, boiling or vaporizing. That we actually have a different formula for. I can't use Q equals mCp delta T for step 2 for boiling or vaporizing because there is 0 temperature change. It's a flat line. There's no temperature change while we are boiling it. And so if I tried to use Q equals mCp delta T, I'd have a 0 to plug in, and that would tell me that it doesn't take any heat to boil something, which just isn't true. So a new formula for you, Q equals M, starts the same way, but then there's no CP and there's no delta T. Instead, it's HF or HV. HF, and that's what these values are. HF is heat of fusion, like for melting a solid or for freezing a liquid. That all happens at the melting point. HV is for boiling or vaporizing. That happens at the boiling point. Or condensing, I guess, if we're going the other direction. So for step 2, I would use Q equals still 20 grams of water, and the HV for water is a value of 2260. 45,200. Now what I have, now it's like I'm right here on my graph, where I had water, I heated it up to its boiling point, and I boiled it, but I haven't yet gotten to 105 degrees. That's step 3, where I am now heating gaseous water. I'm heating steam. It's above the boiling point, so I know it's a gas. I am heating again. It's a diagonal line again, so I can use Q equals mCp delta T, but I'm going to make sure I use the CP of a gas this time. So Q equals the mass of 20, CP of gaseous water is 2.02, and the change in temp just for that step is from 100 to 105. That's a change of 5. there we get 202 joules. So I know how much heat it took for step 1 and for step 2 and for step 3. In order to answer this question as a whole, I need to add all 3 of those up. Give me a moment. All right, so to get my final answer, I would do the 5434 plus the 45,200 plus the 202. These are all in joules. And I would get 50,836 joules. If you prefer, you could say 50.84 kilojoules, rounding it. And then when I ask the question with this absorbed or released, you have to literally write the word absorbed or released. So we went from 35 up to 105. Did the water need to absorb heat to go up in temperature, or did it release heat to go up in temperature? It needed to absorb it. So you need to write the word absorbed. All right, another example for you. 15 grams of steam at 100 is cooled to a temperature of -15. So we know that we are steam at 100. We're cooling to -15. Am I going to pass through either the melting of the boiling point? Well, I'm starting at the boiling point. That'll give us something interesting to talk about. And yes, we will have to pass through 0, my melting point, in order to get there. So this question says we have 15 grams of steam at 100. That is important. If it just said water at 100 versus steam at 100, both actually coexist. Liquid water, gaseous water, both exist at 100. Since we have steam, that tells us it starts as a gas. And so before I can start cooling its temperature down, I have to, the opposite of boil, I have to condense that gas at the boiling point, which is where I already started. I'm going to start in this case with a flat line. Condensing that gas, it was a gas, now it will be a liquid. That's an L for liquid. Once I have liquid water, then I can start cooling it down. But once I get to 0 degrees, it's going to stop because that's the melting point. And at the melting point, it will freeze. And after it freezes, we can cool it some more until we get to our ending temperature of -15. So I have a gas going to a liquid. That's a phase change for step 1. It's the phase change at the boiling point. So I'm going to use Q equals mHV. HV is always for the boiling point. We have 15 grams, and the HV is 2260. So for that first step, I get 33,900 joules. Now you'll see this graph is kind of going the other direction than the last graph. That's simply because we're starting at a high temperature going to a low temperature. If you wanted to draw it the other way, it doesn't matter. But that's why we started at 100, because that's where this problem started. You don't have to do it that way if you want to pretend you're going from -15 to 100. Our second step, we know we're a liquid because what we just did in step 1 was condense that gas into a liquid, since we're at the boiling point. And we are cooling a liquid down. So for heating or cooling, we use Q equals mCp delta T. Whereas Q equals mHV or Q equals mHF, those are for our phase changes. So 15 grams, again, we know we're a liquid, so I'm going to use 4.18. And for the change in temperature, I just want for this second step in black here. So from 100 to 0, that's a change of 100. I did 100 minus 0, bigger minus smaller. And I get 6,270 joules for that second step. My third step is happening at the melting point. It's a flat line for a phase change. That means instead of heating or cooling, I'm using Q equals MH, but in this case, F. HF is always for the melting point. 15 grams. The HF for water is 334. 15 times 334 gets me 5,010 joules. And then this one has a fourth step. Unlike our first example that didn't, this one has a fourth step. We're below the melting point in the fourth step. That means we're a solid. What happened in the third step? We went from being a liquid to being a solid. We froze. So I know it's called the melting point, and you're like, why is it freezing? At the melting point, both freezing and melting occur. Freezing is liquid to solid, melting is solid to liquid, but it's that same line segment. So step 4, it's a diagonal line. That means I'm cooling or heating. And I use Q equals MCP delta T. We have 15 grams. Now we're a solid, so I actually use the CP of solid water and the delta T of 15. How did I get 15? 0 to 15 was the change for this step. Bigger minus smaller, 0 minus negative 15 is 15. We are always going to have positive temperature changes the way I'm teaching you how to do this stuff. So this was 4 steps, and I would add it all up to get my final answer. 33,900 plus 6,270 plus 5,010 plus, oh, I didn't actually total this one. 463.5 would also get added into that. And we would have a total of 45,643.5 joules. We have to say, is it absorbed or released? And that all depends. Were we getting hotter or colder? Here we went from 100 down to negative 15. Therefore, we must have released heat, and the word released has to be a part of your answer. If I had made a slight tweak to this question, if instead of starting at 100, we started at anything above 100, 101, 137, anything above 100, we would have had one step prior, so let's say it was 110, where we would cool the gas from 110 down to 100. That would be the longest a problem would ever be, 5 steps, because you have heating or cooling of a solid, liquid, and gas, phase change from a solid to a liquid, phase change from a liquid to a gas. So 5 steps would be the most, and that would be if you're going from above the boiling point to below the melting point, or vice versa. 5 steps would be the most. Go try.